I'm at British Steel at Rotherham, and in this furnace there are 200 tons of molten steel. It's going to end up as motor cars. 5 minutes ago, they didn't know what the composition of this stuff was. And now, they're ready to make the final adjustments to the composition by adding some material to this ladle. So, what's happened in the last 5 minutes that they found out the composition of this material here? I'm going to show you what's been going on in those 5 minutes and how they've been able to analyze this steel.
Now we have to analyze this sample. If we make the steel one electrode of an electric arc, we can examine the light from this arc. In the spectrum of this light, we find lines. These lines are the atomic spectra of the elements in the steel. So with atomic spectroscopy, we can determine what the steel contains. To ensure that we have not analyzed a lump of impurity in the sample, 2 analyses are made. A computer checks these 2 results and averages them. Within a minute, they are printed at the plant for the operator to decide what to add to the steel.
17 manganese. Trev, get me 700 of silicon up, will you, please? And 1600 of ferromanganese, and we'll take it round by.
Reliable.
And the composition of the steel should be right. In another 3 hours, they'll have another furnace ready to pour. And in a few weeks' time, this stuff will be rolling round as motor cars. And they've been able to find out in just 5 minutes what the composition of that steel is. And that's all been done with atomic spectroscopy.
That was a rather dramatic example of how we can use spectroscopy. Let's have a look at the spectrum we got from the steel. Here's a black and white photograph of the steel spectrum. It consists of lots of lines. It's an atomic spectrum, and each element emits lines of characteristic frequency. That's how we can analyze for up to 30 elements, by looking at these lines. By now, you'll have seen an atomic spectrum for yourselves when you looked at the mercury lamp with your hand spectroscope. I can see the blue, green, and yellow lines. But do atomic spectra of all elements consist of lines? Yes, they do. Take neon, for example. Here's its spectrum.
But look at this. A white light from a hot wire produces a spectrum which contains all frequencies. A continuous spectrum from red to violet. And the way we produce the spectrum? Using a prism like this. Your own hand spectroscope also contains a prism. Now the sun, of course, emits white light, but if you've looked at its spectrum, you will have seen that there are dark lines in it. It is not continuous. Well, why? Here are some simple experiments which will help us to understand that.
First, we'll pour some mercury into the dish and look at the shadow of the dish illuminated in mercury light. But compare what happens when the dish is illuminated with white light. Look at the wispy shadow cast in mercury light. It seems like rising vapor, which is just what it is. Although mercury is present in the air above the dish at a concentration of less than 1 part in a million, the vapor still casts a shadow. It's very effective at absorbing the mercury light. but there seems to be no shadow in the white light. I'll come back to that later. Is this behavior unique to mercury? Well, another element whose line spectrum may be familiar to you, if you've been looking at street lamps with your hand spectroscope, is sodium. Its spectrum is dominated by one strong yellow line. Let's try that shadow experiment with sodium vapor. Here's the setup: a sodium lamp, a flame to vaporize the sodium atoms, and a screen. Let's put the sodium pencil into the flame and see what we get on the screen. Just like the mercury atoms, the sodium atoms in the flame are casting a shadow. They're absorbing light from the sodium lamp. Now let's see what effect the sodium atoms have on white light. Apparently none. At least there's no shadow. But is that misleading us? Let's examine the spectrum of white light after it has passed through the flame. Now there's a dark line. Compare its frequency with the strong yellow line in the sodium emission spectrum. The dark line shows that the sodium vapor is absorbing radiation from the white light, even if our eyes can't detect it. The same thing applies for mercury. Although white light seems to be unaffected, some frequencies are absorbed. Incidentally, why is the sodium flame yellow if it's absorbing light? Well, most of the sodium atoms are absorbing light, but just a few are emitting, and that's why the flame is yellow. Now to interpret these experiments, consider emission first. In the sodium lamp, the atoms are given energy, and this energy is taken up by the electrons. To take an analogy with a more familiar experience, I can say that in the atom, the electron has been pushed uphill. Then as it falls downhill, it gives out energy. But it's clear that the analogy is not perfect. The electron can't lose energy continuously. It can only lose energy in specific packets. It's as though the electron jumps between two levels in the atom. We call these energy levels.
Here are the two energy levels. I'm only showing two, although there are many levels in the sodium atom. An excited atom might have an electron in the upper level. If there's room in the lower level for the electron, it can jump down to a more stable position to give a lower energy arrangement of the atom. As it does, the energy difference between the two arrangements is emitted as radiation. So I'll show the spectrum above the energy levels. The energy difference between these two levels is equal to the energy of a photon of yellow light. And the electron ends up in the lower level, which in this case is the most stable arrangement of the sodium atom, the ground state. Let's see that again. The excited atom, the photon emitted, the ground state atom. Well, absorption is just the opposite of emission. We use a white light source, and most of the atoms have an electron in the lower of the two levels. The light provides the energy to excite the electron in the sodium atom from the lower level to the higher level. As it is excited, the atom absorbs a photon of yellow light, because again, this photon has the energy equal to the difference between the two levels. This time, the electron ends up in the upper level. Let's see that again too. Ground state atom, photon absorbed, excited atom. So we can interpret a spectral line as an electron jump between two energy levels, down for emission and up for absorption.
Well, what does a complete energy level diagram look like? Let's build one from the spectrum of the simplest atom, hydrogen. The chances are you won't have seen a hydrogen spectrum. To produce one, all you will need is a hydrogen discharge lamp and a spectroscope, which is nothing more than a narrow slit and in the body of the instrument a prism to disperse the radiation. The spectroscope almost shows you by its shape how the light is dispersed. If we point a camera in, we should see the spectrum. Focus up. If you expected a simple pattern of lines for this simplest of elements, you shouldn't be disappointed. We see only 4 lines falling into a converging pattern. But is this the whole picture? Remember that what you're seeing here is limited to what your eyes can see and what the television camera can pick up, only the visible part of the spectrum. If instead we display the spectrum on a fluorescent screen, we should be able to see whether the series continues into the ultraviolet. Now you can see the picture is more complete. The lines in the ultraviolet, on the right, are making the fluorescent screen glow a pale blue. The lines get closer and closer together at higher frequencies and seem to fall into a pattern, eventually converging completely. We call this pattern of lines a series, and this one was discovered almost 100 years ago by a Swiss school teacher called Balmer. He thought there could be other series of lines in the hydrogen spectrum, but wasn't able to find them with the equipment available at the time. Well, this simple pattern of lines in the Balmer series invites a simple explanation.
Now remember that line spectra are produced by energy jumps. So how do we interpret a series of lines using energy jumps? Well, first I have to assume that the energy jumps which produce this series all end at the same energy level, here. To see how the lines are produced, let's get rid of the spectrum. I'll start with the electron jump which produces the red line. Here's the next level in the hydrogen atom. To produce the red line, the electron has to jump from here to the lower level. As it jumps, it emits a packet of energy, a photon of red light. The energy of the red photon is the energy difference between the 2 levels, and the electron ends up in the lower level. If I'm assuming that all the energy jumps in the Balmer series end up here, at this lower level, the blue-green line must arise from a jump from a still higher energy level. Again, the photon is emitted as the electron jumps down, and again the energy difference is equal to the energy of the photon. Now all the lines in the Balmer series arise from energy jumps to this level, and we notice the lines in the spectrum get closer together at higher energies. So I must show the energy levels getting closer together at higher energies too. The next 2 lines are in the violet region of the spectrum. The electron in the upper level, emission and energy jump, the electron in the lower level. And so we build up the energy level diagram. Upper level, emission, lower level. And then into the ultraviolet, with the levels getting still closer. Upper level, emission, lower level. Of course, these jumps don't all appear separately in the same atom. There are many atoms in the lamp, and many are excited. So electrons are continually jumping from higher to lower levels, emitting energy as they do. So to depict what occurs in many atoms, all of these jumps produce the Balmer series. But was Balmer right in suggesting that there might be other series? The way to find out is to look at other regions of the spectrum. When we do, we find that there are other series, several in the infrared region here, and one in the far ultraviolet, beyond this spectrum, the Lyman series. Well, on the scale of this spectrum, the Lyman series would be in your next-door neighbor's garden. The frequencies of the Lyman lines are much higher than the frequencies of any of these Balmer lines. And to account for those, we need more than the energy level diagram that we've constructed so far. There has to be an energy level below the lowest level here. With this lowest level, which is the lowest level in the hydrogen atom, we can account for the Lyman transitions. Each transition in the Lyman series is an electron jump from one of these levels down to the lowest level. Well, this is the complete hydrogen energy level diagram, and we number the levels from 1 upwards. So we can interpret spectral series with energy level diagrams. But in our study of spectroscopy, we are not restricted to light that we can produce in the laboratory. Each star has its own spectrum. If we want to examine the spectrum of a star, we can't merely point our spectroscope at the night sky. First, we have to find our star and single out its light. At the University of London Observatory at Mill Hill, we see Mike Doretsky and student Jerry Jacobs doing just this. Here is what our turbulent atmosphere does to the pinpoint of light from a star. And we're going to photograph the spectrum using the spectroscope on the end of the telescope.
Right, that should be the correct position now, I think.
Okay, I've got the plate. Right.
The telescope should be pointed towards the star so that light falls on the spectroscope slit.
All right, we will now test your accuracy. Ah, we've got a star. All right.
Oh, how about that?
Good. In fact, you're almost dead on it. Right. Okay, let me just center this up a bit.
There's the star on the slit now.
Okay, I'm ready to start trailing.
Better.
Yep. Slide out. Shutter open. Go. Time is 9:45 exactly.
And how long will this exposure be?
I reckon 10 minutes.
Right.
The telescope moves to scan the star along the slit.
Right. Well, as this is the first of the night, we better check our exposures and
Right. I'll
see
go
if
and
that's
develop it
good.
straight away then.
Right. Okay, the next star is one.
I've got here a photographic enlargement of the spectrum we took the other night. I'd like to try and classify it.
It's a very, very nice spectrum.
It is
Terry.
indeed, yes. It's come up very well indeed.
Well, I have a sequence arranged in temperature order from hot to cool
Yes.
of a set of stars of standard types which have been observed with the same equipment. Maybe we ought to see if we can fit yours into the sequence.
Yeah, I see. Well, the lower spectra here are clearly quite different. The metal lines are very prominent in these lower ones,
Yes,
whereas
look
in
at
this spectrum
this
they
one,
aren't.
that one.
Yeah. So if we try to fit it in with the upper ones, you see the hydrogen lines are very prominent in all these. So perhaps a good fit might be with this one, do you think? It seems to run
It's
quite
not
nicely
bad. I think perhaps notice the hydrogen line is weaker than both of the stars on either side.
That's
And the
true.
metal lines, like this one, appears to be
Yes, they're
stronger.
a bit too
So
strong.
perhaps it's actually not quite in that position.
Perhaps slightly the lower sector.
Yes,
Yeah.
let's line these up. Now that's a much better fit. Now you notice that this now, the hydrogen goes in a sequence.
Yes, they,
Notice the metallic lines now are going in a sequence, getting stronger.
yes, I think this is probably the best
This
case.
must be the fit. And in
Yeah.
fact, I happen to know that it is.
Yeah.
But I think that we'd really like to learn a little bit more about this star. A photograph like this is all very well, but perhaps something a bit more quantitative is needed.
Indeed, perhaps I can make a densitometer tracing of it and see what you can find then.
I think that's a good idea.
The original spectrum was recorded on this glass photographic plate. With a densitometer, we can measure the intensity of each line in the spectrum by passing a thin beam of light through the plate and measuring how much is absorbed. By recording this, we get the intensity of each line in the spectrum. From these intensities, we can more accurately calculate the temperature of the star. To find out what the star contains, we use an enlarged spectrum and measure the wavelength of the lines. Now we can get a closer look at the spectrum with a microscope, which moves along it horizontally, called a traveling microscope. Notice that there are three spectra: the white lines of the star spectrum in the center, and the dark lines of the reference spectrum of argon above and below. First, we find the positions of lines of known wavelength in the argon spectrum. Then we compare these with the positions of lines in the star spectrum and identify the elements producing them. In this way, through their spectra, stars reveal their temperature and the elements that they contain. Stars, steel, and the structure of atoms. All things we can investigate by means of their spectra. Before I finish, I'd like to show you how this all began with the invention of two devices: the spectroscope and the Bunsen burner. Introduce a salt into the flame of the burner and examine the light through a spectroscope. This was how two German scientists, Kirchhoff and Bunsen, carried out the first experiments in atomic spectroscopy. One of the salts they looked at was this. In this blue flame, they discovered something startling. And in the next television program, you'll be able to see what sort of discoveries were made in the middle of the last century by studying colored flames and their spectra.